So today is our last conversation about statistical methods, and I want to focus specifically on the experimental design, and even more specifically on test calculation, because we had a lot of questions about this already yesterday, and it is true that this is one of the most frequent questions that I get. In fact, this is probably okay. So, can I use 3 patients? Did you see this YouTube video about my grant is due tomorrow? Can I use 3 patients? So this is a difficult question to statisticians. So what I would like to do today is to show you how we actually think about these problems. And it doesn't necessarily mean that you will be able to do all of this, this afternoon, but at least I hope that it will allow you to communicate with your collaborators in terms of what are the important things to think about when we start designing the experiments. So what I would like to do is to talk about sample size for class comparison, and we'll kind of review a little bit what we had before for two-group comparison, and especially in the context of multiple testing. And then we will kind of try to see what happens when we have more complex designs with different layers of variation, and how we can evaluate different types of experimental designs and compare different sources of variation with that. Okay, so first of all, let's just review a little bit the t-test. So remember, we're talking about the fact that we need to have multiple replicates, right, to carry out the inference. And so the important thing is that it allowed us to, replicates allowed us to see how much variation we had within the group, and if we have more variation, it means that we had more likely to have the change, which would be the artifact of random variation. We have less variation, it is more likely to be a systematic change. And we would have biological replicates and technical replicates. We will be trying to distinguish them today. So again, to review what we do to analyze this data, and so when we design the experiment, we need to think about how the data will be analyzed. We are building the signal-to-noise ratio, where we look at differences between the means, dividing this by the standard error of this difference. So this is the variation associated with the first mean. This is the variation associated with the second mean. And so we try to compare the signal to the estimate of variation. So this is our signal-to-noise, and we overlay this on this distribution, which tells us essentially the expected range of values that we would have if, in fact, there would be no difference between the groups, and if all of our data points are independent. And if it falls in the middle, so in the bulk of this range, then we'll say, okay, there's no deviations from our assumptions, so there's no evidence against the null hypothesis. Otherwise, we reject the null hypothesis. And the last piece also to review, because this is important for us for sample size calculation, is statistical power. So now if we look exactly at the same thing, so at the range of values here, and if we put all the alpha in one tail, so this will be the red area. This is the area where we would reject the null hypothesis, right? So let's say we kind of forget about the other tail for the moment. So this distribution is the same as here, right? So this is the distribution which we would expect to see if there was no difference between the groups. Meaning, if the two groups are the same, our means would fluctuate randomly around 0. But if instead the protein abundance in group 1 is larger than in group 2, then the signal-to-noise ratio will not fluctuate around 0. It will fluctuate around some other value which is positive, right? Because y1 will be larger than y2. And so this shifts the actual possible range of the signal-to-noise to the right. And if we make the decision based on this cutoff, so the area under this distribution, so this is the distribution which we will actually see if, in fact, there was a difference between the groups, will be larger. So this blue area is the statistical power. So the power is the probability of rejecting the null hypothesis when, in fact, there is a difference. So this is the probability of finding the difference when it exists. So the red area is the probability of false positive if there is no difference. The blue area is the probability of a true positive change when it exists. And so what we want to do usually when we design experiments, we want to fix alpha to some value which is predefined, let's say 5%. and then we want to maximize the statistical power. So how can we maximize the power? Well, essentially what we want to do, we want to shift the distribution to the right as much as possible. And we can shift it in different ways, right? So first, if in group 1, the protein was upregulated substantially, right? So then this difference would fluctuate around values which are further away from 0. So then this distribution will be really to the right, and this power will be really large. So the first thing is that having a large difference between the groups makes it more easier to detect this difference. So this maximizes the statistical power. So the second way of doing that is to look at the denominator, right? And say, okay, what if we can somehow reduce the variance associated with y? Sorry, yes?
So common notation for type 2 error is beta, right?
So, this actually varies. So so the reason why I'm using this here is because I'm using this points of significance collection. And that's what they, and I see already here that I have, no, that's, yeah, so I have type 1 error is 1 minus beta, and I have it as beta here. Yeah, I have a typo, so this will be 1 minus beta.
Right.
Here. So this is correct, and this is power, this is type 1 error, so this should be 1 minus beta on my slides. So the reason why I have a typo probably because different sources use different notation. So alpha is very standard, but sometimes people use beta for power, and sometimes they use it for the type 2 error. And I think probably there was a mismatch between what I was trying to do and what the book was doing. So, but the power is this, right? And the type 2 error will be 1 minus beta. Okay, thank you. Good catch. Yeah. So, okay, so in addition to shifting this to the right in terms of the signal, we can also shift this to the right by reducing the variance, right? So if the variance in our populations is smaller, it means that also our signal-to-noise ratio will tend to be larger. How can it be done? For example, if we can control some technical sources of variation in our experiment, this will reduce the overall variation. So this helps us increase the statistical power. And then the third way of increasing the power is to have a larger sample size, right? So it's in the denominator or the numerator, so it is going to shift this distribution to the right as well. So larger fold changes will give us larger statistical power. Smaller variation, biological or technological, will give us larger statistical power. And larger sample size will give us larger statistical power. So these are the three things we can kind of dial to make sure that we can detect the changes with high probability. So this is to review a little bit, but now we'll kind of look into this a little bit more in detail. So how do we calculate the sample size? And there are really two ways of doing this. This is a very classical, traditional way to do this, which is really one-liner in R, for example. And in fact, in MS Stats, this is what we use. We use this type of calculation. But what you can also do, and in modern kind of studies, this is increasingly appropriate, is to use simulations. You can actually generate data which would have properties that you would expect from your own experiments, and then analyze this data and see how often you find the true changes, build in different changes and so on. So I will show you an example of that as well towards the end. So, but this is just a very simple classical approach which people used before they had powerful computers. And so what we will do, we'll fix the probability of a false positive discovery, so we will fix alpha. We'll also fix beta, so this is, yeah, so I see now I have a mismatch in my notation. So we fix the probability of the true positive discovery as well. I would fix the anticipated fold change. And these three things, they're easy to fix just kind of culturally, like what is the standard in the literature, right? What is standard? What, in terms of fold change is, what is the minimum fold change that you're interested in, and so on. And then the difficulty is those two errors. So this is how much biological variation, how much technological variation you have in the experiment. So those, it's really hard to know in advance. So what you would typically do, you would look at your pilot studies or historical studies to estimate that. And in MS Stats, what we usually do is that every time we analyze a new data set, we view it as a pilot study for something else. And we'll estimate various components from that, and we will then use this for sample size calculation. And so from this point, there is a very simple formula which is derived kind of using similar arguments as this, right? So if we make some assumptions, we know what the expected range of signal to noise should be. So here as well, if we know these things, and if we make some assumptions, then we know that to guarantee this alpha and this beta and this delta, the variance, so the noise associated with the difference between the groups, has to be bounded by this quantity. So it depends on delta, it depends on beta, it depends on 1 minus alpha. And so now what we need to do is to, for any experimental design and any type of allocation of resources, we need to figure out what the variance is, and then we bound this by this quantity. And so, for example, in the t-test, we just wrote this, right? We have, this is the variance, this is our noise, right? And it has to be bound by this. And so now all of these things are related to each other, so we can fix everything except one thing. And so we can solve for the last thing. So for example, here, if I want to assume that I want to have the same sample size in both groups, so both N1 and N2 are equal, what I can do is to write this as the same constant, right? And I can solve for N. And I say that N has to be larger than this quantity. So now we see that S is the variance. I also assume that S is the same variance in both populations. So it's really easy to see, right, that if variance is larger, sample size has to be larger. If fold change is larger, sample size has to be smaller. And you can kind of also look at the kind of relevant alpha and beta to see that if we want to have larger power, we need to have larger sample size. So you can kind of look at it like that. And so this is how we make this plot. So this is a really simple formula that you can write in R. And we looked at this already yesterday. So essentially, the smaller the fold change, the more individuals per group we will get. And of course, it requires us to understand how much variance we have. And so this is what we use. We learned from the prior studies. And this is where we have to be careful. Remember, we were saying yesterday that if our variance is estimated from a small number of replicates, we can actually underestimate it. And so then it would be a problem.
So Z beta, I have Z1 minus.
This is correct.
That is
Yes,
from,
this is correct. Yes. So if you
that
set.
is- That is from the tables, right? From
Exactly. These are the quantiles of the normal distribution. So, and R will know them, right? This is the Q norm of beta, right? To Q norm from 1 minus.
Right.
So these are the quantiles. So for example, Z1 minus alpha divided by 2, it's exactly this, right? So that the distribution, so Z is the value, such that the probability to the left of this value is 1 minus alpha over 2. So you have alpha over 2 to the right, so to the left will be 1 minus alpha over 2.
And Z beta.
And
is-
beta it will be the same thing, so it will be corresponding to the beta. So that's exactly where it comes from. So it comes from our decision. No? Okay, so this is how we calculate. And so now what it means, I kind of showed here we can solve for sample size, but we can also say, okay, I have a fixed sample size. You know, I cannot really change this. So then you can solve for delta. And you will say, what will be the smallest delta that I can actually reasonably detect with that? And so sometimes we do that as well. When our collaborators say, this is all I can afford, I have that many runs, or I have that many samples. So then we say, well, what is my reasonable expectation of this experiment? We will say, oh, you can only detect a, I don't know, 3-fold change, right? So then we will decide if it's useful to do this or not for this thing. Okay, so this is how we can kind of do it here. So now another thing we talked about yesterday is the adjustment for multiple testing, right? And we talked about the fact that when we have more than one protein, we essentially have to be more conservative. Because now we need to control the probability of making errors in a list of proteins. And so if we want to make sure that the probability of making at least one mistake in the entire list is controlled to, for example, 5%, we have to be more conservative, right? And we talked about Bonferroni correction. Yesterday we said it was too strict, and we talked about false discovery rate. So this is a different criterion which actually allows some false positives in the data, but we control the proportion of false positives in the list. And in fact, the average proportion. So what if we kept collecting the data and analyzing the data the same way on average over multiple data sets, this will be the proportion of false positives that we have. And this is, I'm just bringing it back here to talk to about how we actually do that. And just like with regular t-test, we have two options to make decisions. One is based on the decision rule. So if our signal to noise is inside or outside of this area, or we can make it based on the p-value, right? Is the p-value less than 0.05 or is it more than 0.05? So when we adjust for multiple testing with false discovery rate, we have the same two options. So this was the original proposal by Benjamini-Hochberg. So what we can do, we can take the p-values for each protein individually, one at a time, and we sort them from least significant, so largest, to most significant, which is smallest. And so now instead of comparing p-value to 0.05 or whatever value we set, let us set false discovery rate, I don't know, 10%. So now Q is 10%, right, 0.1. This is our false discovery. And so the most significant one we'll compare in the same way as one for other. We'll take 10% divided by the number of proteins. This has to be really conservative. The least significant we will do without any adjustment. So we'll take 10% and we compare this p-value to 0.1. But everything in the middle will have this kind of changing scale, right? So essentially we start from no adjustment and we progressively adjust more and more so that in the end we have to compare to more and more strict cutoff. And if we start from the least significant, we say, is my p-value less than 0.1? No, keep going. Is it less than 0.1 multiplied by number of proteins minus 1 divided by number of proteins? No, keep going. And the first time I say yes, so now this is protein number k. I compare the p-value to 0.1 times k divided by the number of proteins. If it's yes, everything else is really as significant so that it is monotonic. So this is one way to do this. Or we can think of the adjusted p-value. So instead of comparing the p-value to FDR divided by something, we can multiply the p-value by m times k. And this is the adjusted p-value which we can compare to 0.1. So essentially the adjusted p-value we just multiply by the opposite of this constraint, of this constant. And the adjusted p-value we can compare to our FDR cutoff, which is 0.1 or 0.05 or whatever you would like. It is a little bit easier because then you can have a simple comparison. You don't need to remember to divide your FDR by something. Does it make sense? So the contribution of this work by Benjamini-Hochberg was twofold. So one was they said, okay, let us be less conservative. Let us allow some false positives. And then the second thing that they proposed is this algorithm, which will say that if we use this algorithm for comparing p-values to this adjusted false discovery rate values, then on average, we guarantee that the false discovery rate will be what we want or even less. And then, in addition, we can also use the adjusted p-value, which now we don't even need to worry about, this type of algorithm. We just adjust the p-value once for all, and we can compare this to the FDR cutoff of 0.1. So.
Adjusted p-values and something like posterior error probability are
Not
two different
at
things.
all. There is no posterior probabilities here at all. I'm really glad you brought it up. So posterior probability is in a very different framework. So what we talk about here for the whole week is what is called frequency statistics. It means that the quantities in the population, everything is assumed fixed. So we say that the protein is either changing or not changing. It cannot be changing with some probability and not changing with some other probability. So we say, remember like my first slides where we say there are two means in the population. They are constants, we don't know them, but they're some constant. It's not like they're varying with some probability or something, they're constants. And so these constants are either the same or they're different. There's nothing in between, right? So this type of approach keeps working in this framework, right? And so we're saying now if we make the decision based on the p-value cutoff, I just want to know what happens if there is a change, and I also want to know what happens if there is no change. If there is no change, it's a false positive, so I want to control that. If there is a change, it's a true positive, I want to control that. So this particular work kind of focused on that and showed just from algorithmically that by comparing p-values to this type of sliding scale is controlling this type of error rate. And again, just to kind of put it in perspective, right? So on the left side, we just proceed as if we did a test with one protein, right? So this m divided by m is just 1, right? So we compare the p-value to whatever 0.1 cutoff, right? On the right side, it's as if we did one for any adjustment. We compare our error rate 0.1 divided by the number of proteins. And everything is in the middle, it's essentially linear adjustment between them, right? So it's a middle ground, essentially, between super conservative one for only and not doing anything at all. And right? So it allowed us to control the error rate, but in a way which is, more permissive. It allows more errors, but we still know how many errors we have. So this is really the idea. And I think this is how it was developed originally, right? So they were looking for middle ground between not doing any adjustment for multiple testing and doing an adjustment which is the one-for-one step adjustment. And then the p-value is just for convenience, right? We just, instead of adjusting our FDR cutoff, we adjust the p-values so that we can use the same FDR cutoff. Does that make sense?
So how does the adjusted p-value here affect beta, and is that most significant?
Right.
That's
So
effective.
so for the moment, we are talking about, so we're talking about here, right? So we're talking about how do we reject or not reject the null hypothesis, right? So what we said yesterday is we need to be more conservative. So we need to essentially move those goalposts a little bit further, right? So that we have more strength of evidence for differential amounts. So Bonferroni will take alpha and divide it by 1,000. So it will move it very much, right? Not doing anything, we know it will not control the error in the entire list. So what they're doing here is for the least significant protein, we'll compare it with this. For the second least significant, we'll move it a little bit. For the third least significant, even more. For the fourth, even more. And for the very last, it will be the same as Bonferroni. And so the idea is that it will give us some false positives. So Bonferroni says no false positives, right? Or zero with large probability, right? So because we're using this kind of stepwise kind of linear process, we will have some false positives, but they will show theoretically that this will allow us to control the average proportion of false positives, which we would actually have.
So basically, you do the test multiple times
Well-
and keep increasing the sample size.
No. So you do tests for every protein, right? So now we're in a situation that we have, let's say you have 1,000 proteins. So you'll have to do this test 1,000 times once for each protein. Except that you don't do it alphabetically, you order them from the largest p-value to the smallest p-value. So you start with the least significant protein, so the protein with the largest p-value. And you compare this as if you didn't do any adjustment. Right? Then you take the second protein, which has the second least significant p-value. Now you adjust a little bit. So you adjust by this. It's very close to 1, but it's not exactly 1. Right? So you divide it by a little bit. Then you take the next protein, which is again the least significant. So now you adjust it again. So it is further away from 1, but it's not exactly 1 over n, right? And then you keep going, and once you arrive to the most significant protein, then you have very strict cutoff, which is alpha divided by n. So that would be very far away here. And so, in other words, if you don't do any adjustment, you will have higher power, but you will have a higher error rate. If you adjust in Bonferroni style at the very end, you will have less power because you're super conservative. So Benjamini-Hochberg is a middle ground. It changes the cutoff for each protein individually, but in the order. Okay? So that's the idea. And then, so this was how it was developed originally, and then it's just kind of tedious to say, okay, for protein 1, I need to compare to, F0.1 divided by something. For the next protein, I need to compare. So instead, you multiply the p-value. So that then every adjusted p-value can be compared to the same cutoff point 1. So you see here, we divide FDR by k divided by m. It's the same as multiplying the p-value by m divided by k. So let's just to make it clear. So for the Bonferroni, we say we compare the p-value. Is it less than alpha divided by m, right? M is the number of proteins. It's the same as saying is MP less than alpha, right? So MP is your adjusted p-value, except that we truncate it to 1 if it becomes greater than 1. So the same thing here, right? So we're saying is our p-value less than k over m times alpha. And it's the same as saying m over k times p. Is it less than? So for false discovery rate, we use q as notation. So here we have just exactly the same thing for every protein, so it's kind of easy, but here it depends on your order in the significance list. So it's much easier to multiply the p-value, and then everybody's compared to q. So that's what we're doing.
So how to intuitively relate, if I'm looking at adjusted p-values, not the p-values anymore, I mean, p-values are somehow intuitive, like 0.05, 5% chance, whatever. Does it hold true for adjusted p-values as well?
I mean, at this point, adjusted p-value is just a score, right? And what you're saying is, if your favorite value of cutoff is 10%, just compare this to 0.1. And you can compare every adjusted p-value in this to 0.1. If instead your favorite value is 0.05, well, then do that, right? So at this point, it's not like you need to be very intuitive about it. It's just a score that
It's the same as with p-values.
Exactly. So I know where your question is coming from, because there's a whole collection of other methods which actually view this from the Bayesian perspective, where the cost of the protein changing or not changing is not a constant, but it's more like it's changing with some probability, it's not changing with some probability. So after you see the data, you will see the posterior probability for that. This is an alternative way of looking into that. We just do not talk about this here. We don't have the time. There are good and bad things about that. So there are good things because you can be more sensitive potentially, but the bad things are that it's computationally less stable. So in our experiments, it really depends on the data set and the proportion of true changes and so on. So in the interest kind of being concise, so this is the method which we find is the most robust in terms of just going with many data sets.
So what should happen with the adjusted p-value across replicates?
Sorry?
How does the adjusted p-value change across replicates?
Oh, but you already summarized the replicates, remember? So the p-value comes from what? It comes from this, right? So you take the sum of all the replicates in one group minus sum of all the replicates in the second group divided by the variance, put it on top of here. So you already summarized all the replicates. I think what you're asking is how it evolves if you increase the sample size.
Yeah.
So if you increase the sample size, you will have more and more power, right? So your signal to noise will be larger and larger. So your p-value will be smaller and smaller. And if your number of proteins is the same, right, then you will be more and more likely to reject the most hypothesis. So if there are recommendations to choose the threshold, pick one. So my recommendation is not to choose it after you see the data. Okay? Choose it before you see the data, but it really doesn't matter. And in fact, it's just enough to rank proteins by the adjusted p-value, and because in many applications you can only have the money to follow on top 10 anyways, so it doesn't matter what your FDR cutoff is, right? But if you have to have a cutoff, just pick it before you start actually analyzing the data. So.
Just to be sure, here we use Q is like FDR, but the Q value normally means adjusted P value, right?
Yes. Yes. So, it's a long story. So, for what we need to talk about here, right? You can use any letter. I just happen to use letter Q for FDR cutoff to distinguish this from alpha, right? You can use any other letter, right? So this is we start with working with p-values, right? We adjust them for multiple testing this way, and we compare this to this cutoff, right? So now you're asking for Q values. So indeed, it is for all practical purposes an adjusted p-value. So the reason why I'm hesitating is because it comes from this Bayesian perspective that we just mentioned, where there's prior and posterior, so there's technically no p-values there. So people who develop this method, they don't like to call it adjusted p-value. But for all practical purposes, it's used exactly the same. It's a cutoff. It compares to a cutoff which accounts for multiple testing. That would be the short answer. Okay, so why I'm talking about this? Because, well, this affects the sample size calculation, right? Because now, I think you can probably already think about this intuitively, that if we have more proteins, we have more opportunities for false positives. So this has to have some implications for the sample size, right? And that's exactly what happens. So now, another reason why I am kind of presenting this paper is because in the same paper, the same authors, they also established this relationship by saying, okay, if I want to have the average power that looks like that, if this is my FDR cutoff, and M0 is the number of true non-changing proteins, and M1 is the number of true changing proteins, then I can actually work out the relationship between the average false positive rate for one protein and the false discovery rate. What it means that now if we want to have a sample size calculation in the context of multiple testing, we can essentially use this formula to calculate the average alpha for the individual protein and then plug it back in from this formula. So there's a very easy connection between the multiple testing and this type of sample size calculation. And what it does is looks like that. So the relationship will be that this is the fold change that we want to detect. This is the number of individuals per group. The solid line is the line we looked at before. So this is how many replicates we would need if we only had one protein in our experiment. And these two lines, this is how many replicates we would need if we had more than one protein. But the difference is that the dotted line is the experiment where half of the proteins are expected to be changing, and this dotted dashed line is another experiment where only 1% of proteins is expected to change. And so we have two conclusions. Not only we need larger sample size when we have more proteins, but it also depends on what kind of experiment we have. So for example, if we have a targeted experiment which has more proteins, but we target them because we expect them to be changing, we would not need to work as hard in terms of sample size as if we work with a discovery experiment where only 1% of proteins is expected to change. And the intuition is, again, that we want to protect ourselves against false positives. If everything is a true positive, there is less opportunity for false positives. We don't need to work as hard. But if we have only 1% of true positives and everything is an opportunity for false positive, we need to protect ourselves more, and this means having a larger sample size in this case. So to me, this is something which is really underappreciated because there's really this gold rush from all the protein lists. But what I'm finding, just kind of from the literature and also from working with collaborators, people don't have enough appreciation that if you want to have longer protein lists you do want, the sample size actually has to follow that. And so you will not get the same result with the same sample size and with a longer protein list. So in fact, I'm personally a big advocate for not trying to increase the protein list at all costs, but rather focus on what is of interest to you in your experiment and filter things out. We had a conversation with one of you yesterday. So how can we filter things out? For example, if you know that some proteins, you don't really know what they are, you know you won't be able to annotate them reliably, you will not be able to follow up on them, just remove them upfront. This is part of your protocol, right? So you do it before you do t-test and so on. But if you know that these proteins or features or peptides, they won't be interesting for you downstream, don't include them in the study because it will help you gain the power. I think there was a question.
It was a comment because it's statistical from the mathematical point of view. It totally makes sense, but for biologists, I'm more interested not in structural proteome, which is like top 500 here, which is you will really find the changes. But biologically, I'm more interested in low abundant protein, which are on the lowest.
This is not a problem at all, but you know what it means. You have to have a sample set that would allow you to do that, right?
I just want to point out that ignoring the lower abundant protein, we will not discover fewer.
I'm not saying ignoring them, I'm saying design an experiment which will allow you to reliably analyze those, which is not the same thing, right? So what I'm saying with the filtering is that, there are cases, well, it depends on what you're going to do with the results of the study, right? But for example, there's a lot of kind of opportunities for what is called a non-specific filtering. So essentially you can filter out anything which does not depend on the changes in abundance between conditions. So for example, if you have, let's say you do some kind of MS1 quantification and you have MS1 feature which doesn't have an ID, there's no point keeping it here if you can't identify it and you cannot work with that, right? Or you have features which are so close to saturation and don't have enough variation, no point keeping them there because they will only kind of, right? Same thing for low abundant, right? So I understand that, of course, this is where the value is, but if it's so close to the noise that's not reliable, you may be better off just removing it based on the intensity. But now, if your experiment really wants to go for lower abundant proteins, don't make any mistakes because you would need a sample size that matches the objective. It's not enough to say, yeah, but I want to have low abundant proteins. If that's your objective, you have to design the experiment for that objective, and this really means a much larger sample size.
Maybe ask a very stupid question.
Please.
But let's say you have a two group and you are interested in a long list of protein and first 50% is not changing at all, or not changing. Is it some mathematical way to remove this?
You can remove them as long as you haven't looked at the full changes. Once you looked at them, it's too late. So you can have a part of your protocol that, let's say you do a DIA, right? I don't know if there's a value in this, but let me kind of, at least from the statistical perspective, it would work, right? That, let's say you do DIA and you would say, I'm quantifying 10,000 proteins and I deliberately remove the first 1,000 most abundant because I don't care.
Yeah.
I would probably want to keep them, maybe it's useful, right? But if you really say you only want to, so in that sense, you would be doing a targeted experiment, right? Because you will be only targeting certain analytes, right? And ignoring everything else. So in actual SRM, you will ignore it experimentally, right? You just won't even select these ions, right? So what you are saying is ignoring them essentially from the data analysis, right? So what you don't want to do is two things. So one is where you look at fold changes, oh, I don't like this fold change, let me remove it, right? And oh, I like this one really very much, let me keep it, right? So that will be a disaster, right? And then the second thing you don't want to do is to have a long protein list, 3 replicates, and then think that this will somehow be meaningful. We saw these simulations yesterday, right? Where you could see that things are either, it's really hard to find the changes, or if you find the changes, you inflate dramatically the extent of regulation and changes. So by the way, this type of simulations can be a really useful way of projecting how likely the results will be reproducible in the future. Okay, so this is for the sample size. So now, complex design. So this is all good, but in many cases, we have more than just 2 groups and label-free comparisons, right? In health disease, we have more complicated things. So how do we go about comparing different designs and deciding what is the sample size? For example, do we need biological replicates or technical replicates or something like that? So in fact, it turns out that this type of framework actually allows you to compare things quite naturally. So let's see. What do I mean by complex design? Several things. So one simple way to increase your power, in addition to just sample size and variance what we discussed, is to have more conditions. And this is something that we actually try to advocate for when we can. So let's say that of 2 groups, you have 5 groups. So what happens then? So in this case, you have 5 groups. They are all, let's say, the same organism. Let's say they're related to the disease, but they're different disease subtypes, right? Or maybe different, conditions that are related. So now this horizontal line, this is the overall mean of log abundance of the proteins across the groups. The individual blue points, these are the actual biological replicates in each condition. And the green boxes here, these are the means in each group, how they deviate from the overall red line, right? So for example, this group, the protein is upregulated, this group, the protein is downregulated, this group is very close to the mean. And so it looks like these are kind of different groups, and maybe we are interested in comparing group 1 and group 2, and maybe we don't really care as much about the last 3 groups. However, what is interesting is if we can assume that each of the groups has the same variance around their own mean, so the means are different in the group, right? But if the variances, the fluctuations around the means are the same, what we can do, we can learn this variation from these groups and use it for comparing these 2 groups as well. So this effectively allows us to increase the sample size, even though these replicates come from different conditions. So it means that our estimates of variation will be more reliable because we borrow the information from other groups to learn about the variation in the groups we're interested in. And so the way we do this, we just write more complex models. So this would be one example of such model. This is the overall mean. This is how each group's mean deviates from the overall mean. And this is how individual subjects deviate from the mean of the individual group. And so we can use this to effectively increase the sample size. Now, a caveat, of course, it assumes that the variance is the same. It may not be the same, so there are, of course, things to consider. But at least kind of conceptually, this is a way to increase the sample size. We can do other things. So, for example, what if we want to include biological and technical replicates? So sometimes we have multiple replicate mass spectrometry runs, or multiple, enrichment steps, or multiple extraction steps for the same biological sample. So this is my old example. This is a new example. So this is one group. I have 2 replicates from this group, biological replicates, and now the black dots, these are technical replicates from the same biological replicate. So what this figure illustrates is two things, that we have two layers of variation. Now we have biological variation and technical variation. But it also illustrates that if we have many technical replicates, but not enough biological replicates, so these two replicates don't represent the entire variation in the population. So even if we have more technical replicates, we may not be aware that we actually have more variation in the population. So we would not be doing a good job. So even though technical replicates are maybe useful, but they do not substitute the being able to sample the entire range of biological variation. So, but if we have experiments like that, which have biological and technical variance, then we can also write a model which kind of is similar like this, right? So overall mean, deviation to the group, deviation from the subjects. So here we can kind of separate this out and say, this is the overall mean, this is deviation of the subject. So this is how the group deviates from the mean, this is how subject deviates from the mean of its own group, and this is how technical replicate deviates from the mean of the subject. So we can kind of write this. So now at this point I'm not going to do much mathematics, but you can kind of imagine how we can write statistical models which would describe this type of layers of variation in them. So this is useful because now it will incorporate all of this, but it will also account for the right type of variation when comparing the groups. And it is also useful because it helps us understand the importance of various types of replicates in the sample size calculation. So this is what I wanted to show. So this is an example. Long time ago already, we had a label-free LCMS pilot study where we were doing some, I think it was glycocapture. It was an enrichment for glycosylated proteins, and it was a study of subjects with diabetes versus controls. And we wanted to understand what contributes to the variation most. So, well, there's of course difference between the subject due to the disease. Then there's just biological variation of the subjects. There may be some variation due to the glycocapture. And then there was just some random technological variation due to mass spectrometry runs. It was a very long time ago where we didn't quite know yet, what's the right way to do this. The enrichment technology was kind of new then, so we felt like we had to evaluate the contribution of all of the sources of variation to the overall conclusions. So what happens then, just like we spent a lot of time in the t-test talking about the variance of this group, standard error, right, so on. We can do exactly the same thing here. So now I have three components of variation, so biological, sample prep, and technological. And it turns out that I can also write out the variance of the difference between the two groups, and it looks like that. So it has all of the three components of variation contributing to the variance of the differences between the groups. But what is interesting is the numerator. So we see that here, for example, for the random deviation due to the measurement error, we divide this by the number of biological replicates, number of technical prep replicates, and number of mass spectrometry runs. So if the only thing that will increase is the number of mass spec runs, it will decrease this component of the variation, but it will have no effect on these two components of variation. If we now also increase the number of sample prep, we will reduce this, but we will not affect this component of variation. So the only principled way to really reduce the variation altogether is to increase the number of biological replicates. And so this is how we compare different designs. We say, okay, we want to minimize inefficiency, right? We want to maximize the information content. And for different layouts, different types of variation, which we can learn from the data, different allocation of resources, we can write this type of variances, and we will see which of them essentially minimize the variance, right? And we will do it maybe under cost constraints and availability constraints and so on.
I have probably a very stupid question. So if I have like 3 biological replicates and I do 3 technical replicates with all of them, and I end up with 9 values basically, would you first, or before I do any statistics, would you first kind of calculate the mean of the technical replicates and then somehow propagate this error, or how do I calculate
This is a really good question. It's not a stupid question, though. It's actually not trivial. So what you say is correct. So, for example, here you can see, right, you can average those black dots, right, and this will be your representative red dot, essentially. Right?
With an error.
Exactly. So, well, so what I'm showing here is the experimental design, right? So this is the population. This is 2 biological replicates from the population. This is the technical replicates, right? What you actually measure is just the black dots. You don't measure the red dots, right? But what you want to understand is how much variation you have between the red dots, right? So what you say is just right. So You can take the average of the black dots here and black dots here. Now this is your kind of estimates of the red dots, right? And then compare them. And this is actually a really good way of doing this, but only in the cases where you have exactly the same number of replicates for each technical replicates, for each biological replicate in each group. If you have a failed run, or if you have a missing value, it will not be an optimal way of doing it. So when you have exactly the same number of replicates, it is called a balanced design. And in the balanced design, the conclusions are exactly as you say, just average things, and things are based on the averages. But as soon as you start having unequal number of replicates for various reasons, including missing values, then averaging becomes not optimal because you give more weight to subjects or conditions with more replicates, less weight to others, and you need to do other things. So these models, and in fact this is exactly how we work with MS stats, so these models, they are equivalent to averaging in some very narrow cases of balanced designs, no missing values, but what we can actually do with modern statistical technology is to work with that in unbalanced cases and missing values. So you really can expand. Okay, but so, okay, and so what we can do next, right? So we can essentially, now, how do we work with that? So this is my formula, right? I say for one protein, this will be the variance for this protein that we have. So I have my pilot study. So here we actually had some 2 healthy individuals, 2 diabetes, multiple sample prep, multiple replicates. We can actually feed this model for each protein. And we'll have box plots of variances across proteins. So here we could see, for example, that sample prep was relatively low contribution to variation. So we realized that it was really not necessary to do multiple sample preps. Technical replicates were kind of present. This was low, kind of, lower mass accuracy instruments, lower technology. I don't expect it to be like this now, right? But this allows you kind of to put your priority into how big these variance components are versus how many replicates you want to have. So for example, if your red variance here is very large, it may help just to increase technical replicates. Maybe it's cheaper, right? And then maybe it will reduce this term substantially. But usually biological variation is the largest. And so the only way to really reduce this overall variance is to have more biological replicates. So this is how we think about different designs. And so when you come to us saying, okay, should I design it like this or like that, right? This is what's going on in our mind, right? We'll actually say what is the variation associated with these designs and what will be the ways to reduce it and what are the most effective ways to reduce it.
Could you maybe comment on the necessity of having technical injection replicates based on whether you maybe do DIA or DPA or TNT? Because I can imagine that the variance is different there.
Right, so what I showed here is very general, right? But this assumes that you have reliable quantitative values. So you have essentially an assay which is well characterized, right? So TNT is one example because your ions are selected for fragmentation stochastically. In one run, some peptides will not be selected, right? So technical replicates then can be useful in the sense that you would not get the same peptides. You just actually get different analytes in different runs. But if in your mind you know that you have very abundant analyte, you are likely to get it. You are likely to quantify it everywhere. Then multiple technical re-quantifications of that are not useful. But in terms of getting new analytes across multiple runs, so that there is a value on that for sure. Or in DIA, for example, if your assay is not very well defined and you have a hard time locating the peak, having multiple technical replicates just to be able to locate the peak and be sure that this is the peak from that analyte and not from something else, it has value, right? But this is not for reasons of actually comparing quantitative values, but it's more like for the signal processing, right? And being able to detect the analytes. But if you have an assay which quantifies things reliably, there is absolutely no reason to have technical replicates. But then specifically, right, so let's say you have cost constraints, right, and you have different amounts of runs, different number of runs possible, different relative magnitude of variances. So you just look at this formula, and you say, okay, what I can reduce and how, what are my cost constraints, what are the availability constraints, and so on. Any questions?
Coming back to the technical and biological
Yeah.
replicates, let's assume I have a perfectly balanced study and I have averaged my technical replicates to get biological values. Shall I then average the biological values again because I need my biological means, right?
Yeah, that's right, that's what you will do.
So I average 2 times.
That's right.
And how do I calculate the final error?
So the variance will be only among the red dots. And this is exactly why I'm saying biological variances are important, right? Replicates are important. So you start by averaging the black dots, right? This is your technical replicates. And so even if you have many technical replicates, you only have 2 subjects. So the variance, the noise in the signal-to-noise ratio you will calculate will be based on the red dots. And so even if you have many technical replicates, your noise will be calculated based on the 2 replicates in this case.
So I ignore the technical variance, basically.
Yeah, that's right. And the reason why I'm saying this because you can show this very formally that this is the optimal decision based on such data. Ignoring technical, not ignoring, but averaging them and using everything else from the averages. But this is really only true when you have very kind of special balanced design. And all of that comes, from kind of classical, traditional statistics where people had low computing power. You could do essentially everything with paper and pencil, But they could show that this was optimal, right? But now we don't really do that anymore because even if you have really perfect design, the same number of replicates, you will always have some missing values and at least one protein. You will always have some failed something, So you can't really rely on that.
And then MS Stats can fix that for me. Because I don't know how to do that myself.
Of course, yeah. So what we will do, and we'll discuss this next week, we will talk about how we essentially develop these models, specifically for cases when we have many features per protein, when we have outliers, we have missing values, we will do all of that. Yeah. So, but the motivation really is that, so what we're doing in MS Stats, we're taking these classical statistics, and then we kind of, upgrading them in a way, right, to be able to handle all of the issues.
So, as your technique varies, like DDA versus DIA or different experimental design, right? So, these random error or the variance components will also increase or decrease, or like how would you exactly know that this step has? How do you identify basically that this has variation, this has variation, this has variation?
Pilot study. So what we did here, it was, so see, you only have 2 subjects in each group. So this was not the actual study, this was a pre-study. So we took a very small sample size, but then we analyzed them very extensively, right? So we actually had multiple preps, we actually had multiple technical replicates, and this allowed us to see, okay, how much variation we have among the black dots, how much variation we have among the red dots, and so on. And this allowed us to essentially draw these box plots, and the conclusion from that was in the future we don't need to do multiple sample preps because this variance sigma square is too small, and so reducing it is not really useful. But clearly this variance is important, so we need to work on reducing this variance by increasing the sample size here. And this is really very, so what is really happening with experimental design? You're essentially trying to predict the future, right? You're saying, I haven't done my experiment yet, but I try to project what my data would look like, right? So how good are we at predicting the future? Well, it depends on how much information about the future we have, right? So in our case, it means how much do we know about how our experiment will go, right? What do we know about the technology? What do we know about the biological samples? So the more prior data we can bring in and we can rely on, the better we will be at predicting what will happen next. Now, if you don't have any of that, you can just do simulations, you can do you can try things out, but in real life, especially if these are really expensive, really meaningful experiments, you want to run the pilot study first, work it out, and then make a rational decision about where to allocate your resources.
So what will be the minimum number of samples for the pilot study?
Well, so that's how you do it, right? That's your formula, and you solve for this given how much variance you have, right? So this is the variance, right, that you want to bound by this, right? So that's how we wrote it. So now in this case, so remember this quantity here, right? So if I do these things now, so I want to bound this variance by exactly the same term. And you decide, you fix everything except one thing, right? You say, if I want to have one technical replicate, right, and one sample prep, it gives you only I, number of biological replicates is unknown. Then you solve for that, right? And you can play, you kind of fixing different things, and it will give you the scenario. So a very common misconception is that I can tell you all, just use 3 subjects, don't you worry. No such thing. It's not possible because it really depends on what you're trying to do, right? In new biology, what's the variation in new technology? And I must also add that it's also the person-specific. So the same biological system and the same mass spectrometer, right, in different hands will look different. You know, well, these are very sensitive technologies, right? And small changes can really have big effects. So I would also like to argue that it's also specific to the person who is doing the experiment. Yeah.
In the function,
In the function,
do you count in the variability like same patient but different days variability?
Not here because you don't have this data. To measure this variability, you would need to measure the same patient on multiple days to learn it, right? So what happens here, you have multiple patients and they're all acquired on different days. So it kind of combines between person and within person variation. But if you want to separately say how much is within person, how much is between people, you need to have multiple people and need to have multiple measurements in time for the same person. Then you can kind of separate this and quantify this separately. But if not, it's essentially a combination of them. Okay, so let's keep going because we're not done, right? So, oh, by the way, here, this is also another way to look at that. So just the same thing. So in terms of the cost, right, and the efficiency. So I can just say in terms of this variance, right, how we reduce that. But let's say I decided to use, I don't know, so let's say I want to have 3 sample preps and 3 technical replicates, right? And I would have, so this is the blue line, right? So it will give me, and 5 subjects. So it gives me, what, 45 runs, right? So 5 subjects, 3 sample preps and 3 technical replicates, it's 45 runs. So this will be the variance that I would have. But if I look at this variance, I will have exactly the same variance if I have 15 subjects, but only 1 sample prep and 1 technical replicate. So it's 15 runs. So here I will get the same variance with 45 runs that I get if I have 15 runs. So this is how you can compare this also in terms of cost, right? So because what will happen is that if you have only 5 subjects versus 15 subjects, you will need to have a lot more replicates here to reduce this variance component, right? So just comparing this, you will realize that you will have exactly the same variability, but at a very different cost in terms of how many runs you will do. So that's another way of doing that. Okay, so the next thing is design with blocking. So what we haven't talked about yet much is labeling technologies, right? But we talked about the fact that if we allocate 1 replicate for from each condition within a block, we can be more sensitive. Remember my example yesterday when we had 1 healthy and 1 disease on the same day and we looked at the differences, right? So this was a block. So another, on the technology side, another very typical blocking technique is labeling. So for example, TNT would be one such technique, right? Where a run becomes a block, where we mix together samples from different sources and we acquire them simultaneously. And therefore, we don't have difference between runs because they're all from the same run. So we can eliminate the variation between the runs. So how do we look at these designs? So actually, this is my example, right, where we compared different days and we looked at the differences between the days. And they're all much more informative than if we compared the mean of this group to the mean of this group. So how could we work with that? So turns out we do exactly the same technique. So we'll write a model which will tell us, okay, now I have, this is the mean of the group as I had before. Now this is the random deviation due to the block, for example, day to day or run to run and whatever it is. Now I have the variation due to the individual, and this is the variation due to the measurement error. And so in my cartoon here, I just have 1 healthy and 1 disease in each day. I did it like that just because I can draw a picture. But in real life, you can have much larger blocks. You can have 5 and 5 or whatever your technology allows. 98 well plates would be really one example of block where you have the same number of subjects from each condition and so on. So these models essentially expand beyond just 1 and 1, and you can write out what would be the contribution of the variation run to run or block to block, what is the biological variation, what is the technical variation, and what is the systematic deviation between the groups that we're interested in. And so again, our goal is to distinguish this variation while accounting for all, so this is the variation of interest, and we need to account for all the nuisance variation here that we have. So we can do exactly the same thing, just like here. I wrote out what the variance would be if we have sample prep and so on. I can now write out what the variance would be if we have multiple replicates from each condition randomized, or they're systematically allocated within the block. And so this top variance component, this is what happens if we completely randomize. Right? So if we completely randomize, we have more variance because here we have day-to-day. Day is the block here, right? So day-to-day variation. But if we block randomize, it turns out that we eliminate the day-to-day variation because we compare things within each day. And so in a more general case, the variance of the block randomized design, when we account for block, eliminates this variance component for the same number of biological replicates.
Just to be clear here, variance that you calculate, is this in this specific experiment, was it a specific protein that you were looking and you had multiple readings on the protein, and then what exactly is the variance term?
Right, actually really good question. So here, what I did was I took box plots, right? So they're summarized. So essentially I fit this model for each protein, right? So you do the same thing because of course different proteins have different biological variations, so on, right? So you literally write a loop. You have 1,000 proteins, you'll have 1,000 times fit this model. So it means that you have 1,000 of those variance components. So here, I just drew a box plot of them, right? So I have 1,000 values here, 1,000 values here, and so on.
So you have, suppose, 3 runs, then you would see protein A in these 3 runs. So instead of that 1,000, there will be
So
3
if I have one protein in 3 runs, and I have like different kind of sample prep and so on, I will have for this protein all of these variance components. For the next protein, I will also have these 3 numbers, which are specific to that other protein. For the next protein, other 3 numbers, and so on. So I have this quantity separately for each protein. So here, if I have 1,000 proteins, over 1,000 proteins, I will have 1,000 of these variances. I'll just put them in the box plot here. So you fit this model for each protein. So this model here has this variance component, this variance component, this variance component. So the output of model fit will be these 3 numbers. I saved it for the first protein. For the second protein, I fit again the same model. I save these 3 numbers for the second protein. And then for the next, again, I have 3 numbers. So this is just for one kind of representative protein. But what you're asking is actually quite meaningful because, you know, if I have 1,000 proteins, I will have 1,000 of those variance components, right? So how do we work with that? So what we actually do in MS Stats, we will take the median, or maybe to be conservative, the 75th quantile, or something like that. And we will just use kind of, you know, to be on the larger side, so on the more conservative side. And we'll just use whatever is representative of the experiment.
So again, in this example, you assume you don't have any kind of technical or sample prep replicates?
Exactly. So
otherwise, it would also be...
And then you have to make it more complicated and so on. So the point here was illustrate the blocking. So we didn't do all these other things, so we did specifically the blocks, or the day, and then individual, and then exactly. Those sets of variance components set for each protein, right? And then I can take the median of those, or the quantile, and so on. What is important really here is that if you compare a design which is completely randomized to a design which is blocked, you see that for the same number of replicates, so same number of runs, you reduce your variance. So you use your resources more effectively. You have more efficiency in your experiment, right? You will be better able to detect differences between conditions without paying more money, essentially, right? Just by allocating the resources optimally and then analyzing the data accordingly. And you can see the difference, right? So it depends, of course, how big is this block variation, day-to-day variation, right? So if this variance is very small in the first place, we had this conversation yesterday. If this variance is small, it will not make much difference. You will make it complicated without much benefit. But if you have really substantial run-to-run or day-to-day variation, blocking really makes a big difference. So to kind of comment on this difference between using, for example, TMT versus label-free, well, a big part of this is, well, do we have a big run-to-run variation? If we have runs which are very controlled, so it would not make a big difference, at least from this perspective. But if we have a lot of run-to-run variation, then it will make a bigger difference. Okay, let's see.
Okay, so I'm wondering for the block, variation, how do you calculate? You use all the samples, like in day 1 and in day 2, or can you use a QC pool to calculate the...
No, you use it from the data. So what you do, kind of the same way as you would have here. So you would say, okay, what is the day-to-day variation? How would you know this? You will average, okay, same comment as before. So in a very naive way, right? If you have completely balanced design, I will tell you about the averages, but that's not what these models do, right? They do it kind of more sophisticated. But you can think of it like that. If you want to know how much day-to-day variation you have, you average things in the first day, you average things in the second day, right? And then you compare the variance between these days. So if all the days are very consistent, so there will be some fluctuations, but it will be not much difference between the days, right?
So you cannot use a QC pool, like I pull all the patient blood samples, I pull 200 patient blood samples in a QC pool, and I run it every day. I cannot use that data to calculate.
Well, the QC is good, but the QC wouldn't account for everything, right? Such as digestion of the samples, right, or other things. So you can actually literally get it from your endogenous features. So if you didn't have day-to-day variation, all of those lines will be overlapping very much, right? And so then you would not see much variation. So this would manifest itself with a small value of this variance. But if they're large, so they're very different, and it's a large variation. So this is exactly how you get this block variation. So what I will do, again, when designing this experiment, I have a pilot study where I will just try to understand how much day-to-day variation I have. If you think that your day-to-day variation is only mass spec, then QC samples can be just fine. But if you think that the day-to-day variation incorporates digestion, and like other type of things, so you probably want to work with the full, with actual samples, right, as opposed to just a subset. So it depends a little bit, right?
Is it possible if I have only one sample per block? If I work, for example, have a DMT experiment, but I have 10 conditions?
Yeah, of course. And in fact, it's a really good design. But then you need to have multiple runs, right? So you will have, let's say you have 10 labels, right? You have 10 conditions. You have one sample from each condition, exactly. You have one. But then you have another run, and you have second set of replicates from each condition.
I just won't be able to compare means. I actually compare.
So what you will do is exactly like what I have here. So let's say instead of having day, you will have a run, right? So you compare health and disease in run 1, health and disease in run 2, health and disease in run 3, and then you compare the differences, right? So let's say you have health in one channel, disease in another channel, in one run, we compare this, right? Then in another set of replicates, health and disease in 2 channels in the other one, right? And so you compare like that. But again, what I'm saying is an oversimplification, which only works if it's like perfect, balanced design, equal variance, no missing values. Real life is more complicated, but also modern statistical technologies can help us fit these models even if they have missing values in balanced cases, all kinds of complications.
How to plot if you have a lot of characteristic in your biological system? Like in my scenario, let's say we have 300 patients, lung cancer patients, and there is a lot of subtypes. There is different age, different treatment sometimes, male, female, different age, and
It's not trivial. So this is where you really don't need to know about your system. My advice is not to overdo it, because you will make it very complicated, and then you can introduce human error. You can also narrow down too much on a particular subtype of your subjects, and you will not be able to randomize it completely inside that. So find a few really important sources. From what I've seen so far, age and gender affect everything, so you can kind of be quite safe there. And from that point on, maybe so what you really want to look for is what can affect protein abundance, right? And if you have things which kind of vary between subjects, but you don't know how much they affect what you will measure, it will be less important, right? But if things really affect the abundance of the protein, so then this will be quite important. But don't overdo it, just like a few things, because the price for this is that you reduce your sample size, right? So instead of having 8 data points, you have 4 differences. So now your method works with 4 differences. So now if you start stratifying it further, you will have fewer and fewer things that you can compare. So yeah, so there's a little bit of price for that. But when you have a lot of technical variation like this, or nuisance variation from biology, is beneficial, because you will be able to reduce the variance.
And also when I block now according to age, for example, then normally I will not have it perfectly balanced. Then I have like 30 older people and maybe 28 younger patients.
But you will be comparing, hopefully you'll have 30 older healthy and 30 older disease. So again, you will be comparing within that block, right? And then you will be aggregating those differences across blocks. Again, I'm saying this only to kind of illustrate how it works, but you won't actually be doing this mathematically, you will be actually fitting the models behind it. But intuitively, in like special cases, it amounts to comparing within the block and then aggregating those differences across the blocks. Okay, let's see. So a little bit more on that. Well, so now again, just in terms of sample size calculation, same thing, right? So we have different variance components. Again, we bound this by this term. We can solve by the number of replicates, and we will see that some designs will allow us to have fewer replicates than others just because they're more efficient, right? Or detect smaller fold changes with the same number of replicates. Okay, so a little bit more on labeling. So this is something that I don't yet see used in practice, but I think people should. And this is inspired to some extent from the old literature on gene expression microarrays, where people also have multiple labels and so on. So a lot of statistical methodology was developed for that, which can be applicable here as well. Let's focus on TMT or iTrack, right, where we have a certain number of channels in a run. So a run is a block, right, in this case. In one run, we have, let's say, so in my example here, I have 5 channels, and I have 5 conditions, so 5 disease groups. So what I can do now, this is exactly what you just asked, right? So I have 5 disease groups, and I have 5 channels. So I can have one subject from each disease group in the run. And so now block is a run. So within one run, I have one subject from each group. In the next run, I have other subjects from each group. In the next run, and so on. This is the most effective design. How do I know it's the most effective? Exactly from these considerations, I can write the variance associated from this design, and it will be the smallest. So this is a good way of doing it. But what happens if instead of 5 channels, I have 4 channels? Let's say I want to use one channel for normalization or for some kind of QC, right? So suddenly I have only 4 channels available. How do I allocate 5 groups to 4 channels? Well, there are many ways to go about this, obviously, right? Turns out that for different allocations, we can write the same type of variance, argument. And this variance will depend on the allocation. So you can compare different allocations in terms of their variances, and you will see that some allocations are more effective than others. They give us less noise. And so we actually worked it out. It's in the older paper. Actually, everything I talk about here is from this paper. We had it over a while ago. So it turns out that if you have 4 labels but 5 groups, what you can do, you can systematically rotate the allocation of samples to the channels in a way that, in this type of format, so that each block always has a different sample, different condition missing. Right? This block misses group 5, here group 4, here it misses group 3, group 2, and group 1. So it means that in each block we have always the systematic pattern that we rotate, right? So that in each disease group has the same number of replicates. Each disease group will always have 4 replicates across 5 blocks. Within each block, we only have one disease group missing at once. So this kind of systematic rotating pattern, we can show that gives us a smaller variance than any other types of allocations. And again, we can show this fully mathematically. And then we can do the same thing. What if we have only 2 labels? You can play with different things, but it's just for an illustration, right? So we can do the same thing again, where it's very systematic, where in each block we have unique subsets of samples missing, and each disease group will be represented with exactly the same number of replicates across the blocks. Now the difference is that here in one block we get all the groups. Here, this type of design requires us to have 5 runs. If we only have 4 runs, we will not have the same number of replicates for each group. So it really forces us to have predefined number of runs. Here we actually have to have 10 runs to make sure that we have the same number of replicates for each disease group across all the runs. So it kind of requires us to rotate the availability of samples in each disease group systematically, but it also imposes constraints into how many replicate sets we need to actually complete the full systematic permutation. But then what we can do, we can kind of actually write out those variances. So for example, in the block randomized design, as I was saying earlier, we just have this variance. Now, these designs that I showed, they're called balanced incomplete block designs. They're incomplete because we cannot fit every group in every block, but they're balanced because we impose, that every block has the same thing missing, and every disease group has the same number of replicates still. And so we see now that we will have a very similar variance component, but these constants, they determine how many labels we have, how many things are missing, and so on. And so we can now actually plot these variances for different allocations. So this is number of replicates per group, this is the variance. This is the variance we would have if we could fit every subject in every block. The red dots are the variances we would have if we only had 4 labels instead of 5 labels. And they're dots because it prescribes how many replicates we can have. We cannot have any number of replicates. And this is what would happen if we only had 2 labels, right? We would again have to rotate the systematically. And so you see now that, for example, here if we had 7 replicates, right, so how our variances would be different depending if we used 5 labels or 4 labels or 2 labels. So this allows us to compare different types of allocations of resources. And this is how I know this design is better than this design from this formal argument. This is really how we think about that. Okay, so this is for label. I added a slide based on the conversation we had yesterday. Somebody asked me about adjustment for multiple testing using permutations. So now I'm kind of going back to what we discussed earlier in the hour when we talked about this, right? So how can we do adjustment for multiple testing with full discovery rate? So an alternative method for adjustment for multiple testing is to use permutations, and the reason why I want to talk about it here is to put it in the context of the sample size calculation. So this is a 2003 paper, it's quite old, and I don't see this method used very old, except that I was reminded that Perseus uses something like that, so that's quite interesting, right? So going back to our previous discussion, so how can we use some alternative technique to control for multiple testing? So what we can do is to have the sequence of cutoffs for discovery rate, let's say 0.01, 0.5, 0.05, 0.1, and so on. And now we will permute the labels of the group. So we're talking about false positives. So if the null hypothesis is true, it means that there is no difference between the groups. It means that the labeling of a sample in the group doesn't really matter. So if the protein abundance is the same between the groups, we can shuffle which sample belongs to which group, and it will not change anything. And so here we permute things like that. Then we will calculate, for example, our signal-to-noise ratio. We will do this many times. We can permute this many times over. And we estimate for discovery rate like that. So for each threshold, we see the average number of our signal-to-noise ratios which exceed the threshold if we shuffle things, divided by how many signal-to-noise ratio exceeded the threshold in actual data set that we have. And so the idea is that when we shuffle, these are all false positives because we shouldn't be seeing any true positives. And so this estimates the proportion of false positives among things which we actually claim as positives. And then we pick this threshold for the desired full discovery. So this is another way to do adjustments for multiple testing, and it's fine, but there are technical issues with that. So we assume that the null hypothesis is true for every protein, so we start shuffling everything, right? And the theoretical properties of this are unknown and so on, but the important reason why I want to talk to you about this here is that this is fine if you have 2 groups or multiple groups, and you don't have any other complexities, such as biological and technical replicates, such as labeling, such as blocking, such as complex designs. So this type of permutations, they really cannot be extended easily to things which are incorporating the discussion that we had, like blocking and different types of variation and so on. So this is another approach to control for multiple testing. I'm guessing that you can do sample size calculation with that just by simulating. However, it will be very difficult to use this type of approaches if we have more complex designs than just kind of comparing groups. So this is just a side comment on that. Okay, I have little time left. But let me maybe go 5 minutes over time, if you don't mind, because I really wanted to share a couple things. So this is quite quick. Pooling. So this is also something which comes up a lot in experimental design. Can I pull together physically samples from different sources? Okay, let me hide this first. So samples from different sources to save the number of runs. And we're not talking about TNT, we're literally talking just combining multiple samples without any labeling and run the experiments on pooled samples. So one idea would be take all the healthy and pool them together, and then take all the disease, pool them together, and then have 2 runs. Is it a good idea? No, right? Because we want all the information about the variation we just talked about, right? So we don't know anymore how much person-to-person variation we have in each condition. So pooling, at least mathematically, it's actually a reasonable idea, but with some caveats, right? So we can do it if we don't have enough biological material, we need to limit runs. So we cannot pull all the samples from each group, as we just said. What we could do, let's say we have 20 replicates in each group, right? So what we could do potentially, let's say have 5 replicates in one group, make a pool, 5 other, make a pool, 5 other, and 5 other. So now we have 4 pools. And then we do the same thing for the second group. So now we will have 4 kind of pools versus 4 pools that we will combine. So in general, this could work. And again, we evaluate this using exactly the same argument. So if I don't pool, I would have, and I have capital I number of subjects in each group. So this is my variance from the randomized design. But instead of each subject, if I actually have R people which are pooled together, this is kind of like averaging, but averaging kind of biologically, right, and physically. So you can show that the variance is actually smaller. So in a way, so in other words, if you have 20 runs and each run is a subject, you will have more variance than if each run is a pool of more subjects, right? Because the same number of runs actually has more biological information. So you're actually using a larger sample size in a way, so you reduce your variation. But then there are multiple caveats from that. So if you make errors like with pipetting, or there's some samples compromised by storage, you compromise the entire pool, right? So there are many kind of things that can go wrong. Also, it limits your choices in terms of the statistical analysis downstream, because now that you average subjects, you cannot do things such as biomarker discovery, right? Remember, we were talking about the fact that biomarker discovery is prediction, right, for individual subjects. Now that you mix together multiple subjects, you cannot do prediction for individual subjects. You can only compare averages. So if you want to do a t-test, you are fine. If you want to do other things, you should not do it, right? And then also there are some kind of technical things, like biological materials are averaged kind of on the original scale, but mathematically we do it on the log scale, so there are some issues, but it's kind of not as important. And so the very last thing I want to tell you about is how we do sample size calculation by simulation. So this is something which we also implemented in stats actually, and we find that some of these calculations that we discussed, well, they make different assumptions. And as we had a question earlier, but what if we need more technical replicates for various reasons and so on. It is easier to build in this type of issues into simulations than it is in the mathematical calculations. And so what we can do for that is to simulate different outcomes of experiments in the future and see which types of experiments are more effective than others. And so I would like to illustrate this, especially because it's kind of the end of my part for this week. So I will shift gears now for biomarker discovery and talk about what if, instead of comparing averages, we want to make predictions for individual subjects. So remember that this is the objective number 3, where we talk about prediction, right? So it's class prediction. And the methods go about making these decision rules and classifying individual subjects as healthy or disease or something like that. And so the methods will essentially draw these decision boundaries, which would use our proteins to decide who is healthy, who is diseased, right? And then they need to, this is a very simple boundary where we ignore protein 1, only use protein 2. Here we use both proteins, we classify it a little bit better. Here we do accommodate our data too well. It's overfitting the data. It kind of finds some of the artifacts which are likely not be reproducible later. Okay, so now we want to know, okay, let's say we want to do biomarker discovery, right? And we want to find what are the proteins that are predicted. So how many replicates we need for that? If we don't do averages, if we actually want to do predictions, so how do we do that? So this particular simulation was based on a study we had in collaboration with the Ebersol lab. So this is a targeted experiment, so it's a relatively small number of proteins. but the advantage is that it had a large number of biological replicates, so we could look at the biological variation quite a bit. So it had 200 subjects only in the training set. So we quantified 70 proteins among 200 subjects, which we could use to build this type of decision rules. And then we had 269 more subjects where we could apply the decision rules to see how well the decision rules actually work on new patients, which the method has not seen before. But we wanted to use that to understand what is the effect of sample size versus the number of proteins. And so kind of you're saying the low abundant proteins are important, right? So what happens, right? So this is a targeted experiment, but some of these proteins were fairly low abundant, so you could kind of see that. Okay, so now what we were trying to do is to understand how accurate these decision boundaries are and also how robust they are in terms of how much they accommodate individual subjects versus how much they find the actual patterns in the data. So if a decision rule like this is very robust and is accurate, it means that, you know, if we have a couple more subjects in the study, a couple fewer subjects in the study, it should make a big difference. So it can be the same thing. So what we try to do is to take, this is our data matrix from the training set that we had here. And Ting, who was here earlier, so this is her work, Ting Huang, a PhD student in my group. So she said, okay, can I pretend that I will repeat the study but with a smaller sample size? So let me just sample randomly some number of subjects here and develop this classification rule from a smaller number of subjects. And then in this case, she used random forest just because it was the easiest, and she would rank proteins by their importance for prediction. She will just keep the top 10 proteins in her list, and she would record two things. One is the predictive accuracy on the validation set, so how well this rule did in the next set of data. And the other is to see what were the proteins which were recorded as the top 10 most important.
How many subjects track of it?
That I will show you in a minute. So we will vary that, right? So let's say we take a subset of subjects, right? We will use them to develop this rule. We will see, okay, how well they did. So essentially in terms of accuracy, right? So true positives versus false positives. And we will also record what are the proteins in the top 10 most predicted proteins. And we will do this 100 times for the same sample size, and we will draw a histogram like that. So here, this is 100 repetitions of taking the same number of subjects in the study. And the bar shows how often this protein was selected by random forest as predicted. So ideally, we would have some really predicted proteins selected 100 times, and then some other proteins selected 0 times because they're not predicted, right? And we will see what happens. So here we go. So we started by taking 10 subjects out, right? So we randomly select 10 subjects, develop the predictive rule, start over 10 other subjects, predictive rule, and so on. And we also varied the lengths of the protein list. So here we said, okay, let's just rank proteins by their average intensity. Let's just pretend we only studied 20 proteins, 40, and then 70 proteins, right? So we only had 70 proteins in the data set. So here's what happens. First of all, with 10 subjects and 20 proteins, the predictive accuracy is not so great. It's 0.5, right? But you also see that the proteins which were selected as predictive, the best of them were only selected half of the time. So essentially, half of the time, some other proteins were selected as top 10 most predictive. Now, if we now keep the same sample size, but increase the list of proteins to 40, well, the predictive accuracy improved a little bit. Probably there are some important proteins in this extra 20. But look at this bar plot, right? So now, only a quarter of the time, these proteins were systematically selected as predicted. And now 70 proteins, look, it's even less. And the predictive accuracy went a little bit up. And now we added proteins and it actually went down. So what happens is that the sample size is too small to reliably detect the decision boundary in the space of more proteins, and it's doing this, right? It's essentially overfitting to the individual subjects. And so next time we have 10 other subjects, it overfits to 10 other subjects, and so it picks up on other proteins. And this is reflected in the predictive accuracy that is not so good. And now we keep going. We can do it for 20, 40, 100, and 200. And so what you see is if you have a relatively small sample size, always the same thing, your predictive accuracy increases a little bit and then it drops. And you also see that the number of proteins which are consistently selected as predictive, well, everything is inconsistent essentially. Everything can vary from one experiment to another. And it's only when you start having a really large sample size, 200 subjects in this case, you see the predictive accuracy is much better, and we have the patterns which are much closer to what we would like to see, that consistently we select some proteins as important and others kind of drop out, meaning that they're less important. So we implemented this type of thing in MSTATs just to allow you to kind of play out a little bit what is the importance of sample size versus the length of the protein list. And again, it is my experience in every single case that larger protein lists require a much, much larger sample size than what is typically understood. And just very last comment, so I'll skip that, and very last comment, this is actually quite interesting because if we move now from detecting differential among proteins to the prediction, well, we still have the same requirements for the experimental design. Meaning we need to avoid bias, we need to minimize inefficiencies and all of that. And this is an illustration of that. So this is a colorectal cancer study from TCGA. And it was exactly the same thing. So in this case, though, it was a DDA study, so it had much larger protein list, 3,000 proteins, and it had 100 replicates. So we kind of tried to do the same thing, rank proteins by their average intensity and change the length of the protein list, and we changed the number of replicates. And so if you see that if you start increasing the protein list, essentially the number of times the same protein is selected as important is like, I don't know, 10%, right? So essentially what it means that every time you select new subset of replicates, you will get new proteins. But if you look here, you see the predictive accuracy is 0.99 and 1 everywhere. So essentially every single protein, no matter which protein you pick, every single protein is super predictive. So what happens, well, the same thing as what we discussed last time. They had colorectal cancer patients quantified in one day, and then controls were quantified in another day. So every single protein is super predictive, but not for reasons we would be interested in. And so in this type of things, you can also see that if you have a flawed experimental design, it will manifest itself like that. And you will probably, if you don't know this and you will run it on your own study, you will have super high predictive accuracy, you will be very happy, but it will not be reproducible in the next study. So no matter what we do, experimental design comes first, because that's really where the quality of the data is determined. And I don't have time to talk to you about assay calibration, because I also think that this is a very common mistake that people do when they do calibration analysis, but you can just look at the slides, and in fact, it is published. Let's see if I have a reference here. Do you have a reference? Yes, here we go. It's MCP 2018, so we have a paper talking about how people make mistakes in linear regression. But I guess for the sake of giving you some lunchtime, I have to stop now. Okay, thank you very much.